Welcome, everybody. Really excited to have you here. Welcome to World Quantum Day Q&A with Intel here on Twitter Spaces. I'm your host, Madeline Littrell-Coyle, and today we're going to be talking everything from spin qubits to commercially relevant quantum systems. Quantum computing uses the power of quantum physics to solve complex problems exponentially faster than conventional compute. It'll solve some of the biggest challenges, like climate change, chemical engineering, drug design and discovery, finance, and aerospace design, just to name a few. I'm joined today by Jim Clark, Director of Quantum Hardware at Intel. Jim joined Intel's quantum computing effort back in 2015. He's co-authored more than 100 papers and an impressive 100 patents, and is a member of the National Quantum Advisory Committee. He's an authority figure on all things quantum. He lives and breathes it, down to the name of his pet German Shepherd, Qubit. Thanks for joining us, Jim. We're excited to have you.
Thanks, Madeline. Happy World Quantum Day to everybody that's out there. Madeline, that was an excellent introduction. I need for you to join my team so that you can explain to the world what we're trying to do here. So thank you.
I love it. I might be applying for a job. So let's kick things off. What is quantum computing and why is it so exciting?
When we think about it, everything in our universe, everything in nature, every molecule, every cell, these are based on the principles of quantum mechanics. Richard Feynman was a Caltech physicist. He worked on the Manhattan Project, has a Nobel Prize, or had a Nobel Prize. And he proposed in about 1980 that we could use quantum mechanics and the principles therein to do computation. In particular, we used two different principles, that of superposition and entanglement, to generate an exponentially larger number of states with which we can compute. A quantum computer of a certain size would be exponentially more powerful for certain algorithms than even the largest supercomputers on Earth.
Wow. Super impressive and highly technical stuff. And we have a fan in our CEO, Pat Gelsinger, and he tweeted in a question, so I want to start it with this. What is the state of quantum computing research at Intel? You're the best person to speak to that.
Yeah, thanks. As Pat knows, at Intel, we are experts at making transistors. We have been following Moore's law for more than 50 years now. We understand silicon, and we understand how to manipulate that silicon into the transistors that we sell today. At Intel, in our quantum program, we have a qubit that's a little different than some of our peers or competitors out there. Our qubit looks a lot like a transistor. Instead of having a current of electrons going through our transistor, we have a single electron. Then we operate our device at a fraction of a degree above absolute zero. In fact, we operate our device at a temperature that is 250 times colder than deep space.
Wow.
And at those levels, we can access the quantum states of that electron and use it to do our computation. Now, to finish with my response to Pat, we are using silicon in our transistors to help us with quantum computing. This is our winning strategy, building on our success of Moore's law to develop the compute technologies of the next 100 years.
Well, Pat says repeatedly, right, that Moore's law is alive and well. But how does Moore's law help you with quantum computing?
Yeah, absolutely. What we do at Intel is we basically piggyback on all of the work that's done here in Oregon at our D1 fab in making the next generation of transistors. The more we make our qubits look like the next generation of transistors, the more we can just ride the coattails of Moore's law to help us out. And in fact, what we do here is we process wafers, qubit wafers that have been specially designed in our 300 millimeter fab. We pull these wafers from our fab. We take them within just a few hours down to our cryogenic testing facility. And overnight, we can study an entire wafer, many, many devices. at single electron levels in the quantum state. We take this information, we feed it back to the fab to make better and better devices. We pick the very best samples from that wafer, and then we study that for computation in even colder environments. So we are using all the tools of our toolbox in Oregon and D1, Moore's Law, and Intel to make our quantum devices.
You mentioned devices. Let's talk about Horse Ridge. What is it and how does it work?
It's not enough just to make a qubit chip. You have to control that qubit chip. You have to send pulses into it. You have to collect information out of it. We're trying to manipulate a single electron in what looks like a transistor. So we need specialized chips to do this. Horse Ridge is our solution to cryogenic control of qubits. This is an Intel system on chip processor that was customized for low temperature on the Intel 16 process. What we do is we take this finalized chip and we put it into our dilution refrigerator, into our cold environment in close proximity to our qubit chip. And by doing this, we have better control over our devices, and we have better scalability of our devices from where we are today to where we will need to be. So Horse Ridge is an important component. It's done inside Intel for controlling our qubit chips.
What would you say is Intel's competitive advantage?
Well, let me first move up the stack a little bit.
Okay.
It's not enough to make a qubit chip. It's not enough just to control the qubit chip. We need an architecture on top of that. You may be familiar, or perhaps not, that a couple of months ago, we released the Intel Software Development Kit. This is a software environment that allows us to schedule, compile, map algorithms to simulated hardware. This, when taken together with Horse Ridge and Control, when taken together with our qubit chip, this provides a full stack. Basically, we are making at Intel all parts of the quantum computer. This is our competitive advantage.
Absolutely. And thank you, by the way, to everybody who is submitting questions live. We're seeing them, we're taking them. So let's take a question that just came through, Jim. What are some of the hurdles that researchers like you face in developing a quantum computer?
Great question. There are there are things that keep me up at night.
Yeah, you're like, the list is long.
Heating is not our friend. Any little bit of heat, we spend a lot of time with conventional transistors trying to reduce the heat, trying to reduce the power consumption. Any little bit of heat that comes out of our devices or Horse Ridge at low temperature can be a problem. The cooling capacity at 10 millikelvin or 100 millikelvin temperature is not that great. So we're constantly up against the heating of our devices. At the same time is, how do we efficiently wire up the many qubits? Right now, the community is at the 10 to few hundred qubit level. We need to get to 1 million qubits. We need an efficient interconnector wiring scheme to be able to control all those qubits coherently. This was something that the semiconductor community, the transistor community, dealt with in the late 60s. Scientists with the last name of Rent from IBM came up with Rent's rule, and it basically talked about how the efficiency of our microprocessors was determined by the interconnects. And this is something we need to do across the entire quantum community, wiring up qubits. That's the thing that keeps me awake at night.
Well, you're already such a pro in this industry. You're such a pro in speaking on the advisory board. What do you see as the current state and the projected timeline of quantum computing?
What we know from Intel, what our competitors are familiar with, is anytime we release a transistor, there have probably been 10 to 12 years of research and development for that new transistor before it makes it to market. We're getting started. It's an important time to start, but we're probably 10 to 15 years away to having a quantum computer that's going to change your life or mine. And this is not unexpected with the complexity of quantum systems. It's not unexpected given the timelines it takes for new inventions to make it to the market, even transistors. So at that time, we will have a computer that can solve problems that just can't be solved by any supercomputer on Earth. What we need to do today is we need to start building the chips. We need to start solving some of the problems that we expect to have. The software development kit that we have, that's going to teach people how to program, how to compile algorithms, how to schedule them to the qubits. So it's not too early to start to be ready for when quantum computing will have an impact.
When we were talking earlier, you talked about how quantum computing is the future, and you're already doing a lot of things at the national level to prepare for that. Can you speak to some of those things that you're doing at the national level?
Yeah, and in 2018, there was the signing of the National Quantum Initiative Act. This was supported by both the House and the Senate, by Democrats and Republicans, and it was signed by the previous administration, by President Trump. It didn't make a lot of news because in DC, news really only occurs when people disagree, but this
Right.
was widely supported. It's been emphasized even further with the current administration. I've had the privilege of being on the advisory committee for both the previous and the current administration. In 2019, there was the first authorization for the National Quantum Initiative, which had money available to NSF, the Department of Energy, NIST, which is part of the Department of Commerce, to fund quantum activities. We're at a point 5 years later where we have to reauthorize that. And there is a group of about 15 people that meet regularly. These are people from academia, from national labs, from industry. I work with many of my peers in the community. And what we're trying to do is we're trying to keep the U.S. competitive in the quantum space, both from a national interest perspective and an economic perspective. And so we're trying to ensure that the government has the right amount of funding and in the right ways to ensure future leadership in the quantum space.
Well, speaking of leadership in the quantum space, many outlets come to you to be a spokesperson about what's going on here. And you recently did an interview with Fox, and I really liked this question. They asked you, what does a typical day look like for you? Could you answer that for us now?
Yeah, if your perception of quantum computing is the Big Bang Theory, part of me wants to say you'll be disappointed, but part of me wants to say it's not too far off. I have a fantastic team of quantum physicists, material scientists, chemists, electrical engineers that are far smarter than me. We get up, we analyze the data that was taken automatically overnight. We figure out our next round of experiments to do. Wafers come out of the fab. We start to analyze them. And we're not only taking the data of the day, but we're taking the data of the day and planning the future. So it's typically a series of experiments and meetings. And we get to see cool stuff literally every day. The amount of data is mind-blowing.
Oh, I can only imagine. What brings you the most joy in your job?
It's solving hard problems, which oddly
Mhm.
enough, those hard problems are what brings me the most frustration as well.
It's that
There
double-edged sword, right?
It is a double-edged sword, and you have to keep in mind that this is a hard problem that we're trying to solve with quantum computing. I'll give you an example. Our quantum bit of information is encoded in a single electron in a sea of about 50,000 silicon atoms. So if you think about that from a statistical perspective, we're trying to control a primary form of matter in an electron in a sea of atoms where those atoms don't have defects or don't disturb the nature of that electron. So oftentimes we don't know what's causing problems or why something works or doesn't work, and we have to do substantial experiments. These are not things where you can look into a textbook and find a solution. We're discovering things all the time. And when we do, it's usually one of the all-stars on my team coming to me, probably late on a Friday night saying, look what we got done this week. Look at what we solved. And usually they're not coming and saying we just solved it. They're blowing us out of the water with the data or the level of result that we've gotten.
Yeah, you're creating the future every day in these jobs.
Some days it feels like the future is coming faster than others, and some days it feels really slow. But yes.
Yeah, I could see that. Well, we have a lot of people here on this Twitter Spaces event, and some of these people are future quantum heroes. So we got a question from one of those. And this question is, if I want to work in quantum, what do I need to do?
There's a misperception that to work in quantum, you have to be a quantum physicist. Sure, we have quantum physicists on our team, but we also have chemists. We have material scientists that know every bond of every atom in the materials that we use. We have electrical engineers that design circuits to characterize our devices. So virtually any part. Oh, and we have computer scientists that figure out how to map and schedule our algorithms. So what I would say is virtually all parts of STEM can map into quantum computing. It's not just quantum physics. We need a diverse team. And that's what we try to build every day, is that diverse team.
Oh, we love to hear that. So if you've got job openings on your team, we've got people who are interested.
It even starts at the elementary level. There's an initiative through NSF called the Q through 12 initiative to ensure a pipeline of people working, even at the elementary school level, working in quantum computing. When you think about it today, if I told you that a quantum computer would arrive in about 2035, the people with finishing their PhDs about that time, they're not even in high school yet, which is mind-blowing.
So it's important.
It is important to reach those people, those students, and get them interested in this technology.
Absolutely. When you're thinking about a 15-year time span on this, it's important to reach into this next generation and start preparing them now, right?
That's it. That's it. We have to spend as much time doing that as we do working ourselves in the future.
Let's go back to talking about the future and what your team's creating. What are some of Intel's recent quantum research developments?
We talked about Horse Ridge, and every so often we have our next generation of Horse Ridge and accompanying chips. Some we publish about and some we're still studying. About a month or 2 months ago, we released our software development kit to developers. This basically gets people programming in our software environment on simulated qubits. And so we take that feedback. We learn a lot from the people using it. They learn a lot about how to use a quantum computer, and we can accelerate our program and quantum computing as a whole. I've talked a lot about the fab today. Every time I get a wafer from the fab, it has thousands and thousands of small arrays. These arrays are only about 12 qubits in size, but we have more than we could ever characterize. So, it's at some point we're trying to increase the amount of characterization we do. We're growing our team. We're looking for collaborators in the academic community who can help study our devices. And we published a really nice work on our 12 qubit chips at the American Physics Society meeting last March in Las Vegas.
Oh, that's exciting. Let's move on to another question we got from the web. Why is Intel investing in silicon spin qubits?
There are two answers for that. Intel is investing in quantum computing because Intel is a compute company, and quantum computing has the potential to revolutionize computing. It won't replace conventional transistors. It will augment them for certain applications. So it's natural that Intel would look at quantum computing in the same way that Intel looks at AI, graphics, neuromorphic, any of these technologies that were once emerging and have now arrived. We're doing the same thing for quantum. There are about a half dozen, maybe more, different qubit types that people are considering. We've looked at all of them. The one that lets us build on Moore's law, the infrastructure, the $500 billion industry every year that is semiconductor manufacturing. The only one that maps closely to that is the silicon spin qubit. I can go into the factory here in Oregon, the D1 factory, and use the same tools, the same toolbox to make my devices. I'm trivializing it a bit in complexity, but we have the knowledge and the expertise to best build these devices.
You mentioned that you want to find partners, especially in academia. What's next for your team and Intel's quantum research?
Just like we do with transistors, we take a stepped approach where the steps overlap. Today, we're characterizing our 12 qubit device. We're finalizing the design of our next larger system, and then we're defining what even the next larger system looks like. And it's an iterative process. As we learn something on our 12 qubit device, we feed that forward to our next device. And we're starting already when we study it to find out what problems we need to solve down the road versus what problems we need to solve today. We used to call this at Intel the TikTok model before TikTok was a social media platform.
I was about to ask you if that was a part of TikTok. Okay. So it's a part of our TikTok model.
This would be the equivalent, the quantum equivalent of the TikTok model.
Okay. All right. And as we're talking about what's next for Intel, what do you think is the next big step for the quantum industry as a whole?
Right now, we're in what's called the NISQ, NISQ, noisy intermediate quantum systems, or something like that. I apologize if I got the acronym slightly incorrect. We have in the community 10 to a few hundred qubits. They're pretty noisy. What we need to do is get that number up to, let's say, a few thousand qubits. We need to improve the qubit quality. And then we need to start doing something called quantum error correction, where we take a group of noisy qubits, we run an algorithm on it to get what is effectively one logical qubit or qubit without noise. This is probably 5 years away and will take a few thousand qubits. Then when we string these together, we can make a larger system. So error correction is the next biggest milestone for our community.
Error correction. Let's transition into Intel technology for a minute. I have a couple of questions coming in on that. What is Intel's hardware approach to developing commercial quantum systems?
Yeah, as I said earlier, what we're doing is we're making our qubit devices just like we make our transistors. We use the same tools to that extent, and we have published on this externally. We use EUV lithography, extreme ultraviolet lithography, to pattern our gate stack of our quantum devices. There are a variety of different technology nodes running at Intel in our R&D facility, and we pick and choose the best parts of each of those nodes to put the puzzle together that becomes our quantum chip. So we are using various parts when needed, the most advanced, and when not needed, relaxed, of our transistor processes to make our qubit chips.
Can you tell us more about the Cryoprober and how that works? This was a new one for me when we were talking earlier.
Yeah, this tool did not exist. Intel worked with two companies, both Finnish companies, to develop a tool to characterize quantum information on silicon. If you think about it, in our community, we have an information problem. We take a chip, whether it's from the fab or a lab, we cool it down overnight, we study it, we warm it up, we put our next chip in there. That's a very slow process. This is not how we do it with transistors. When a wafer comes out of the fab with transistors, we characterize the full wafer. We get statistical process control in the matter of a few hours. We decided that we needed something like this for quantum. And so we have a full wafer. It's 300 millimeters. It's a hybrid tool of half refrigeration and half prober. And within a couple hours, we can take a 300 millimeter wafer and cool it to 1.6 Kelvin. That's 1.5 degrees above absolute zero. And then overnight characterize thousands and thousands of devices. And so this really provides us the information to feed back to our fab to make better and better devices. And it allows us to select the very best devices to feed forward for even colder temperatures where we perform the quantum computation.
It's amazing when you're talking about this level of chill and this level of cold that our devices and our fabs need to be. It's unfathomable to me.
Well, Madeline, we think of ourselves as pretty chill and pretty cool in the quantum group here at Intel.
I think that needs to be your social media bio if it's not already. All right, I have another question on our technology. How is Intel preparing for post-quantum cryptography?
So one of the biggest applications for a quantum computer is cryptography. It's breaking codes, not unlike the Turing machine or various systems that we have. In fact, the typical cryptographic scheme that most of the world uses, the RSA key, is something that a quantum computer of a certain size would be very efficient at breaking. And so emails, financial transactions would all be vulnerable. So at the same time, governments around the world are racing to have a quantum computer to play offense. There's also the notion of what sort of cryptographic scheme should we use that would be a good defense against a quantum computer. This has also been part of the current administration in DC, their quantum initiatives. It's actually being led by NIST as part of the Department of Commerce. And the variety of companies, including Intel, are working on post-quantum cryptographic schemes to protect information once a quantum computer arrives. Obviously, you would want your post-quantum cryptographic scheme to arrive faster than the actual cryptographic-ready quantum computer.
Jim, I just want to ask you this last question in the last 60 seconds before I close. How does it feel for you and your team to be making history with Intel?
no one, no one's asked me that. No one's asked me that.
You weren't prepped for that question,
I
huh?
was not prepped for that question. What I will tell this, and my team, I hope that they would listen. Is when I look back, when I look back over the last month, it feels like we haven't done anything. When I look back over the last 5 years, I am absolutely amazed at how far we've come. And I hope that when we have a system that is of commercial relevance to Intel and the community, that we look back and are just astounded by what we've done.
Well, I know we're all astounded by what you've done, and it reminds me of a quote that Pat says a lot. That what is it? Sometimes it takes a decade. Sometimes it takes a decade to make a week of technology, and sometimes a week to make a decade's worth. Something like that. I'm probably butchering it, but
You
but your
typically
team
do
feels that.
less than you expect in a year or so, and far more than you expect in a decade.
Yeah, well, we're really proud to have you and your team on board at Intel and excited to hear about all of the progress you've been making. So, thank you for being here today.
And happy World Quantum Day.
Happy World Quantum Day to those who celebrate. It looks like our time has to come to a close because we're right here at 1 o'clock Central, my time. I don't know about you all, but this last half hour has absolutely blown my mind. Thank you, Jim, for giving us a taste of what the future will look like. And I can't even imagine all of the amazing things quantum will help us overcome and achieve. So for Intel, I am Madeline Littrell Coyle. Thank you all for listening. Have a good day.